Okay, hello once again. So in this video, as promised, we will actually go now and turn some of these power supplies on to see how the charge to mass ratio experiment behaves. So the first thing I'll turn on over here is the heater for the electron source. If I turn that on, sort of get that going, and hopefully if you look very closely into this back region here, you see a little bit of glowing in there. I see sort of an orangish glow back in here and sort of up around here. That's the glow of a hot piece of metal. Okay, and of course a hot piece of metal glowing means electrons are jiggling around and could potentially be liberated. In this case they are. It's not very different than an incandescent light bulb, nothing very sophisticated about it, just a piece of metal getting hot because of the current running through it, because of the power supply that I just turned on. Okay, this one back here. So the power supply really isn't much of a concern for us. We could even set it to the back. There's no adjustment on it. It just sort of sits there and keeps the piece of metal nice and hot in there for the electrons to come off. Okay, and so then the next thing we'll do is like, where's the electron beam? That's kind of the exciting part about the experiment. And we haven't accelerated the electrons yet. So we'll go down here to the high voltage power supply and we'll turn it up to something like, let's just go to 2000 volts or so. So I'll turn up to about 2000 volts there. Okay, so if you read very carefully on the device there, it's sort of the number of voltage coming out divided by 1000. So 2.0 is 2000 volts. Okay, so that's on. And now, lo and behold, if I go back to the Helmholtz coil, you can see that I see an electron beam in there. That's the bluish beam. So that's the electrons being colliding with the helium in there, giving me a color I can see. And so you can kind of see it all coming together. In fact, if I sort of look, see that little glowing slit right there? That's sort of the outer metal sort of encompasses this hot glowing incandescent object inside there, again, likely a piece of metal or something. So I can sort of visualize that the electrons will be sort of spewing out this way and pulled this way by the accelerating potential. So there's my electron beam. It's kind of cool. I can turn up a bit more, like if I go to something like to 2200 volts, 2300 volts, you see it gets even brighter because electrons are traveling faster, likely more collisions with helium atoms in there, making it brighter. And likewise, if I turn the voltage down again, there's about 1000 volts. See the beam starts to get kind of dim. That's about 1300 volts. It gets kind of dim. You can still sort of see it in there, but the electrons just aren't traveling as fast anymore, and the collisions are sort of what they are. So we'll leave it nice and bright like that for the sake of this video here. And so now what do I do next? Well, I have the electron beam in there, and what I can do next is start sort of fiddling around with the Helmholtz coils. That's the last parameter in there. So I'll sort of move it down a little bit so you can see the ammeter and some of the controls here. And so what we'll do then is I will turn up, let me just go ahead and close the switch first of all. So I'll close the switch so the magnetic field will be one way or the other. As I mentioned, it'll be sort of a position we can loosely call up and down, but we'll see what happens. Now what I'll do is, of course, the voltage knobs on the power supply are wide open, and I will start to turn up the current now. And so if you want to watch either my hand turn the current knob up or watch the electron beam over there, well, maybe we'll focus in on the electron beam because it really isn't that interesting watching someone turn the current knob. This is where all the physics would be. So here we go. I am now turning up the current knob, and you can see that the electron beam starts to bend. Isn't that cool? And so this is what we mean by the measurement. So obviously this switch position is that we'll call up. So there's current, sort of really high current right there. So that's about almost 2 amps going through the Helmholtz coils. If I back off quite a bit, get something like that, there's about 0.3 amps. I'm just reading this off of this little red meter sitting right here. No magic involved, but that's what the point of it was there. And if I turn the current down to 0, of course, the electron beam is undeflected. So it's like a little video game. You can just sort of sit here and mess around with the current. There's a whole bunch of current. There's like 2.5, almost 3 amps. And again, there's something like 1.3 amps. So you can sort of mess around with that. But if you go down to 0, of course, you can only go so far. So let me just turn the beam up like that. And so now what I'll do is I'll go back to that switch I was telling you about, this switch right here, and I will switch the switch to the other position. So 3, 2, 1, bang, like that, other position. So the current stays about the same, but now if you go back to the Helmholtz coils, you can see that the beam is now in the other direction. So why is it in the other direction? Because the current now is traveling in the opposite direction, so the magnetic field inside the Helmholtz coil is in the other direction. So I can do the same thing. I can sort of get my hand back on the current knob. There's 0 current, and I can just sort of see the same thing. There's about 1.8 amps or something going through there. So you can see, indeed, the magnetic field, which is either into the screen or out of the screen, is causing the electron beam to turn in circles, as it should, according to the law F is equal to Q V cross B. And so in this situation, given that you know the electron beam is going this way, going this way and there are electrons, you can use the right-hand rule to determine what direction the magnetic field must be to cause the electron beam, say, to deflect downwards in this case here. Now, it might be something you should include in your analysis or your report, remembering that electrons have that negative charge on them. So that in a nutshell is sort of it, okay? And let me just show you a couple of other parameters here for the experiment. So what I'll do is let me just get some decent amount of curvature right there of the magnetic field, of the electron beam, about a ½ amp. And of course, what I can do now, I'll leave that, and what if I sort of decrease the accelerating potential? So what I'll do is I'll turn it down by 100 volts. I'll go from 2300 volts down to 2200 volts. Not much change. 2100 volts, not much change. Let me turn it down a lot. Then so there's 2000 right there, and let me turn it down to about 1000. You sort of see that the electron beam is getting a bit dimmer in there. I can barely see it. And here we go back to the 2000 higher volts, so you can see it there. So there's 2500, 2100, 1500, and so that's sort of what effect it would have on the beam as you lowered it. There's about 1000. That's about as low as you can go for any visuals in there. And if I turn it up again to around 2000, then the beam sort of appears. So that's sort of maybe what I anticipate you would do is if you approach this in person, you would sort of fiddle around with, the high voltage power supply over here. You look at the beam, which is pretty cool. The room could be darker, but it looks okay the way it is. And then some of the power supplies over there. Again, this one isn't turned very much, but you are turning the current knob quite a bit over here and the direction of the switch in there. So what the plan is then for your data, I will show you in subsequent images here. What I've done is I've taken a bunch of data, set everything up, and I've selected accelerating potential values and currents through the Helmholtz coils, and I've taken images of those. And so what you would do is you would see the beam on the grid doing something like this, and what your job is for your core data is you need to estimate the radius of this beam. You need to estimate what radius of circle these electrons are traveling, and it'd be a pretty big circle, right? You're just seeing an arc of it here. So I'd imagine like if this was just part of the arc, the electrons, if they're allowed to continue, would go up, 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 like all the way around. I know my pencil's off screen, but I'm coming back around again, and it might very well come back around like this and then rejoin the actual beam you see. So the electrons are making a big circle. All you see is an arc of it, but you need to be able to get the radius of this arc, including its uncertainty, for your calculation. So knowing what radius the electron beam is traveling in, given the value of the high voltage and the magnetic field strength in the Helmholtz coil, allows you to determine the charge to mass ratio. So that's what your job is going to be. So you'll get a bunch of images, and you should get in there as the directions show, either by hand or using some software called ImageJ, or perhaps some way with MATLAB or something, to start grabbing some XY points off of this beam in calibrated units like centimeters. So if you get a bunch of points that are along a circle, you should be able to use some fitting routine either in MATLAB or Python or Mathematica or whatever you're doing to get the radius of that beam, including its uncertainty. And once you have the radius of the beam, then you can proceed with your charge to mass ratio calculation. So that in a nutshell is the charge to mass ratio in operation. We have a high voltage power supply selection that we can make. We have a current we can set in Helmholtz coils. We have a directionality switch that we can choose. And you can just sort of see the entire thing operating. Even in this sort of relatively bright room, I can see the beam going up and down. And then when it's up or down, then I can change the current and sort of change the radius of the beam that I see there. All sort of a function of the accelerating potential. And that's what we have. Okay? So the subsequent work then would be to start digging through some of the data that's been taken for you and start retrieving the radius of the electron beam as a function of the accelerating potential and the magnetic field strength.